What are the theoretical limits of quantum error correction? Imagine trying to keep a delicate message safe from all the noise and interference around it. That's what quantum error correction aims to do for quantum information. But how far can it go? What are the ultimate boundaries that define what quantum error correction can achieve? These are the questions we're exploring today. Quantum error correction is all about protecting quantum data from errors caused by noise and decoherence. These errors happen because quantum bits, or qubits, are very sensitive and can easily lose their information. The main goal is to find the maximum error rate that a quantum error correction code can handle while still keeping the data safe. This maximum is called the error threshold. If the noise level stays below this threshold, the code can correct errors indefinitely by increasing the number of physical qubits used. But if the noise exceeds this limit, the error correction fails, and the data gets lost. The limits of quantum error correction are rooted in principles similar to classical error correction, but they are more complicated because of quantum phenomena like superposition and entanglement. One key concept is the hashing bound, which sets the maximum rate at which quantum information can be reliably stored or transmitted through noisy channels. Approaching this bound means the error correction method is nearly optimal. Different quantum error correction codes, like surface codes or color codes, have specific error thresholds. For example, surface codes can handle physical qubit error rates of about 1% under certain noise models. If the physical error rate is below this, logical qubits can be protected for long periods. Achieving this requires a lot of physical qubits, sometimes thousands or even hundreds of thousands for each logical qubit, making resource overhead a real challenge. Advanced codes also exploit degeneracy, where multiple physical errors lead to the same logical error, making decoding more efficient and pushing performance closer to the theoretical limits. But there are practical constraints too. Error mitigation techniques, which aim to reduce errors without full fault tolerance, face fundamental limits that restrict their scalability and effectiveness as systems grow larger. Researchers are working hard to develop codes and algorithms that get closer to these limits while minimizing the number of physical qubits needed. Understanding these boundaries guides the design of fault-tolerant quantum computers that can perform complex calculations reliably despite hardware noise. In essence, the theoretical limits of quantum error correction are defined by the maximum error rates that can be tolerated, the efficiency of the codes, and the resources needed to reach these goals. These limits shape the future of quantum computing, pushing us toward more reliable and scalable quantum machines.